Yeah, recording has started. So, good morning, all of you. So, I hope the screen I'm sharing is visible. Can you please confirm it once again?
Yes, sir.
Yes, sir.
Okay, thank you. So, yesterday, not yesterday, day before yesterday, in our last class, so we have discussed about, right, this couple of things, right? C amplified with emitter bypass capacitor. And right, we have also taken one example and like one design example, right, to see or to investigate if some criteria has been given, some design parameter has been given, right. So how to come up like with the complete configuration, complete circuit configuration, means what should be the values of this RC, RE, like RC, RE1, RE2, all those things that we have like that, those things we have come up, right, like from scratch. But here a couple of things, for example, what should be the value of this RS and all these things, I think that we have not investigated. So generally, typically this RS value should be yeah, this RS value is actually the resistance offered by this source. So typically it is quite less compared to the other resistances that you are using in your circuit. Okay, and this is not type of like you are including, right? But you are using some source, signal source. The signal source will offer that RS. Huh? So yeah, if you know about the signal source, you should be able to find what is the resistance or that is offered by that source. Right. So I think at the last of this, means at the end of this last class, we have started our discussion on this AC load line, but we have discussed it quite briefly. So let us start it again in today, right? And try to understand what do we mean by DC, what do we mean by AC load line. DC load line, it is already clear to you, right? So AC load line, comes into the picture when the AC, the circuit become different for DC signal and AC signal. So what do you mean by DC signal? The circuit become different for DC and AC signals. So for example, let us consider this particular amplifier circuit, right? So here we can see like these are the coupling capacitors. If you want, you can take probably like add one capacitor here, add one capacitor here before you take the output, right, before you take the output, so that you will get only the AC signal here, not any DC current should flow through this if you want. Then in that case, that is also possible, right? So you're getting output from here, and you have splitted the emitter resistance into two parts. One is RE1, RE2. In last class design, we have seen that typically this RE2 is much greater than this RE1 because we need RE1, RE2 means the total RE for DC stability. However, if we have higher value of RE, that will reduce the gain of this amplifier, right? So one way would be to bypass the larger part of this RE2 by using a capacitor. So for example, if you now consider, if you are considering this circuit, this amplifier circuit, and if you see its AC equivalent circuit here, right, then you will see that AC equivalent circuit is look something like this, right? Here, I think you will recall that all the DC voltages, like here, you have to ground, right? So this all the DC voltages are ground here, so that and the capacitors has to be like shorted. That way, capacitor is being shorted, right? So this is the AC circuit, right? Okay. Now, if you consider now, if you have to suppose draw the load line. Load line means IC versus V of C. If you are considering the to draw the load line in the output characteristics, then this is the output characteristics IC versus V of C. So this is the load line, this is the DC load line. However, right, however, if you see okay, that will come to the DC load line maybe after some time. But if you now see this loop, and for to draw the load line, we know that this IC is flowing, right, this IC is flowing thing, okay, like it's from here, and V of C is this one, right? So here this is IC, V of C. So we have to take the KVL across, means along this loop, right? Along this outer loop of this circuit. So you consider the KVL along here, and then this is for AC. Then similarly, you have to also consider the KVL for DC along this output loop. So this is for the DC condition. So you see that for DC, what is happening? This for DC, all this capacitor has to be open circuited, right? That way open circuited. This is open circuited, and this signal source is gone. Right now, here also we are taking this KVL along this outer loop, right? Along this from V1 to V2. So apply KVL
Sir,
along here and apply KVL along here. Yes.
sir, there was a capacitor on output, sir, but in DC we just take it same as the AC part
There was a capacitor. Which
at the
capacitor?
output terminal.
Oh, at this output terminal.
Yes, sir. So, sir, in DC means we will not get our V output. So,
Right. We don't need actually V output from here. You are right. In DC, actually, if you have a capacitor, then basically from here we will not, the V out port would not be there, right? V out would be open circuited, but what I can do in that case, you see this is an wire, right, that was connecting from here to here. So this wire will obviously there, right? So after that it will be open circuited. So V out has been open circuited, but you will still have this wire connected from here. If you really want to measure the DC voltage, you can probe it here, right? Isn't it? Is my point clear?
Yes, sir.
Okay, so see here again, I think that was a good question. So suppose if you are probing, means if you are connecting, suppose say you have a CRO here that you will be doing in your laboratory, right? So if you have a CRO and say you have connected this and CRO has two probes. So say one of the probe is grounded, okay? The other probe, say this one, now you have connected from here, from this. Then what you will get in that, okay, let me use this red line only. So in that case, what you will get an amplified signal. If this signal is an sinusoidal like this, then here this signal would be like this. Okay, this is not that way symmetric signal. So let me try to draw it in a, yeah. So it will be like this. And here this potential would be zero. So this is the 0 volt. Across this 0 volt, you will get this ups and downs, right? It's the amplified version. And there will be 180-degree phase shift. You know that, right? Now, say in the other case, one of you, means one of your friend has probe, not this probe is not connected here, but you have connected the probe over here, right? Then what you will get? Then what you will get is something like this. Then also the signal would be like this, right? But this potential would not be 0 volt, right? But 0 volt would be somewhere here, right? And you will get here this VCEQ, right? So across this VCQ, you will get that because you are now will get both the DC as well as AC from here, right? If you are probing it from here. But if you are probing it at this after this capacitor, you will get the DC part would be blocked. You will get the only the AC signal.
sir, there would be no shift in CRO pi shift.
There will be no shift in CRO. What do you mean by that?
Means the pi shift is only due to the this transistor.
Uh, Pi shift is due to this transistor due to the amplification. Yeah, better to say that because of this amplification. Because you can understand, right? If this signal
Yes,
increases, right, then
yes, sir, that
IB
decreases.
increases. Yeah, if IB increases, IC increases. If IC increases, then this
This
voltage, right? It
decreases.
is basically
Yes,
like, you can say like V1 plus V2 minus of this voltage, right?
yes,
So
sir.
if IC increases, then this voltage has to drop. So that way you are getting this 180-degree phase shift.
Sir, so what does CRO do? Means it just shows the signal.
It just display the waveform.
Okay, sir. Okay.
Okay, it just displays the waveform. Okay. So, and from CRO, you should be able to find like what is the, means it has certain knobs, both amplitude knob as well as this time division knob. By using adjusting those knob in a proper place from the signal, you should be able to find what is the amplitude of the signal, right? what is the DC value of this signal. That should be also care. If you are choosing it carefully, adjust, or if you have adjusted the CRO carefully, then you should be also able to find what is the DC level. And obviously from the sinusoidal signal, you should be able to measure what is the amplitude of the sinusoidal signal. At the same time, you can also measure the time division. So from this time division, you should be also able to find what is the frequency of the signal. So yeah, after today's class, I will post one video, okay, from that we have made, like that I have made in our basic electronics lab on the CE amplifier. Okay, so where let me, I think, go to some of the previous, um, just a minute. Yeah, not this one. Have I not drawn that circuit earlier? Yes, I think I have drawn it. Just give me a minute. One minute. I think it is after that. Yeah, it is like, it would be similar to this circuit. Huh? This circuit. It would be similar to this circuit. So in lab, what we do, we use this one signal source. Okay, that signal source is also will come from the signal generator. Okay, so from signal generator, you can give sinusoidal signal, you can give triangular type of shape signal, you can give square signal. Huh? So it is possible to give this type of generate this type of signal from the signal generator. And from the signal generator, you can also vary what is the frequency. That means the time period of this type of signals. You can also vary the amplitude of the signal. So usually signal generator are here. Then intentionally we also use on RS so that we know what is the value of RS. Then we will use on coupling capacitor. Then on voltage divider type of biasing for CE amplifier, where we have two emitter resistors RE1, RE2, and this RE2, across RE2 you will connect one capacitor. Okay, that is called the bypass capacitor, right? And you will take the output across from here, huh, through a capacitor. So you'll take the output from here, right? And there, okay, I will show you in that video that if you are, okay, first thing is that let us fix the signal. Okay, let us fix the amplitude of the signal, and let us fix also the frequency of the signal. Okay. Then if you fix this signal source, okay, from the function generator, then I will show you that what is the gain in this condition. In this condition means when the capacitor is being connected, you will see a higher gain, right? Then we have a knob here, type of switch here. Then you open the switch. Okay, that means this capacitor is now disconnected from here. Then you will see that suddenly the gain has fallen. Okay, and typically how we do that, it's good that you have bring this in this context, so that will also help me to discuss. So how we will show it. Okay, so suppose we have a CRO, huh? This is the CRO. You will be able to see how the CRO looks like in that video. Okay, so CRO, it will have some display, right? And it will also have some adjusting knobs, okay, for to adjust like what should be the time division, what should be the time division, what should be the amplitude division, and also there are some other functions in the CRO. If you also want a more description on the CRO, then also we have another video that we have recorded in our lab, which demonstrates the basic functions of CRO. So if it is if you are not aware of much of the CRO, I can also share that link with you so that you can go through that video, and it will clearly demonstrate like how CRO works inside and how you should operate this CRO in the laboratory. Okay,
Sir,
so and huh.
sir, is this CRO same as oscilloscope?
It is actually CRO stands for cathode ray oscilloscope. So it is actually oscilloscope only.
Oh, okay, sir.
Okay, so CRO, but oscilloscope can be of like this is a cathode ray type, means you have you have an like electron source, right? Then you apply this signal across this horizontal and vertical deflecting points, and you move the signals, and there is a fluorescent screen here, right? And you move the signal and the fluorescent screen will go glow. So that's how you can see the signal, okay, in this type of CRO. But there is also another type of CRO, which is the digital oscilloscope. So that in there you don't need this electron beam to to be electron beam to be fall on this screen, fluorescent screen, and to show, means to visualize the waveform. Okay. So, and as you know, in earlier TVs also, it is the same similar type of mechanism like previous TVs, right? Previous television sets. There you have an electron gun source, and then all this, and then you have a screen where in that screen you are able to see like what is going on, right? It will continuously do the scan at throughout, means along this screen. Right. So, and as you have seen earlier, this cathode, like earlier TVs, with that what you said, the width of the televisions used to be quite large, big, right? Because cathode, for a cathode ray, it has to have some electron gun, then high voltage accessories, then the deflecting plates. Then also you have to have some amount of distance, so that from this cathode ray you should be able to scan from the top of this screen to the bottom of the screen, as well as from the left to right. So that way it should have some particular length, and that is the reason why earlier television used to be, the width used to be quite thick, means the width used to be quite large. But this, you now consider this now LCDs and all this type of televisions, there it is like very thin, right, compared to the earlier televisions. Now the same thing also is there with the CRO. If with oscilloscope, if it is CRO type, means cathode ray oscilloscope type, then obviously it's with means along this direction. Okay, this along this direction, this width will be quite thick. However, if it is of digital oscilloscope, then it would be like quite thin, maybe say up to this much. Okay. Okay. And there are two more things, that is called the channels. So you have different number of channels in different CROs. So typically what we use in our laboratory is a two channel CROs. Two channel means you can visualize two waveforms in this screen, right? So say this one channel, will should have two pair of wires you should connect with for it to make one channel. So if you connect it across and signal, it will show you some wave from here, right? And then another, these two, if you connect across another signal or another voltage source or something like this, then you will be able to see another signal visualize here. And there is a knob here. Using this knob, you should be able to adjust like the height of the signal. Means you can suppose the signal is here like this, then you could have moved the signal like this. Okay, you could have moved the signal also down. Means you can do this vertical movement, right? Uh, okay, using this knob. So that way you can, carefully trace out two signals here. Okay, so suppose here we are feeding here, the signal is the source signal, right? Then source, if it is source signal, then what do we do in our laboratory? We see the source signal. Say the source signal is like this. Okay, then here we will connect the, say, the output signal. This output signal we connect across this, and there we will see the output signal. So output is bit type of amplified if both of them are having in the same amplitude scale, right? So this is in the amplified. So you, from here you should be also able to see that there is a 180-degree phase shift. So you can see both the input signal and output signal on the same screen, right? So from that you should be able to find what is the gain, what is the phase shift, right? All this stuff, right? And so that is how we will do it in our lab experiment for this as well. So here this one channel, this channel we will connect with the source, and the other channel we will connect with this output. So one will be connected with the output, other one is means between output and ground. right? So if you do that, then you should be able to see this type of waveforms in your screen. Obviously, I am expecting that you have given sinusoidal signal in your VS. Right. Now, if what will happen when you fix it, and if you change the the switching position, so that once you are connecting the CE and once you are disconnecting, then you will be able to see when you have connected the CE, when CE is present, the gain has the gain become higher. So probably the gain become something like this. Okay, nothing will change except the gain. Okay, the gain will be higher. Now, when you remove this, means disconnect it, you will see the gain will fall. And that is also what we expect from this right, from this circuit, from our analysis, right? Now this is one thing. Now in our board, the values of RE1 and RE2, these are fixed, right? So you cannot change them. But suppose if you are making this total circuit in your breadboard, and you could have also changed the values of RE1, RC, and all these things. So if you have changed those values, then you will see that the values of the values of RE1 or RC, that will also do an effect or show an effect in the output characteristics, right? So all these things you should be able to see in that video. um, uh, and one more important thing is that is we are going to discuss today. That is, now we have fixed the signal, right? Now what is what we are going to do? We are going to change the frequency, the frequency of the signal. So when you change the frequency of the signal, you will also notice that the gain, okay, the output gain is also dependent on the signal frequency. Okay, and for a certain range of frequency, you will see the gain is type of flat. Means if I am plotting here gain and versus frequency. So if you plot, we will see that in the for some certain region the gain is flat. Okay, but if you go for very low frequency, we'll see that the gain will fall. And if we go for very high frequency, then we also see the gain will again fall down. So that way you can, you have learned about different filters. So that way you can guess, like you can see that it is the behavior is almost similar to that of this band pass filter, right? For lower, it is the gain is falling down. For higher frequency, the gain is also falling down, right? Similar to that characteristics, right? Gain versus frequency characteristics, right? So you should be able to see that. Now here one question it might arise in your mind, that how we are finding here gain. So how we can quick that you can obviously do, you can measure this amplitude and you can measure this amplitude. So this is basically the gain. So that way in your laboratory you plot, you change the frequency of the signal and you get the different points, and that how you plot it. But in your experiment, the video I will share with you, there you will be able to see that if this is the input signal, right, and this output signal, when you are changing the frequency, so initially say the gain is like this, right? If you make the frequency very high, then you see the signal frequency very high, then you will see the signal frequency is very high, right? So the signal will become something like this. So you can see that obviously from here you can guess the gain is reduced, right? So it should be clear. Please go through that. That is a very small video. Please go through the video once I share, and you will be able to visualize. I mean, you will be able to see what I am talking about. That the exact same thing what I am talking about, that you should be also able to see in the laboratory. Okay, so let us now come back quickly to this. Right. So here, what? Yeah. Now, if you take now we have started our discussion on this AC load line. So and we have plotted this AC equivalent the AC circuit, means it is not the small signal circuit, AC equivalent circuit, and we have also plotted the DC equivalent circuit. And if we allow now consider this output loop, right, for these two AC and DC, then you will see for here DC output loop we have three resistances, RC1, RE1, RE2, right? However, if you see for this AC, then we do not have, we have only RC1 and RE1, because after this point this is grounded, right? So we have only these two resistances, RC and RE1, right? And you know that RE1 is much lower than this RE2. So that way, if you now find what is the slope, okay, before going to that, now how can we write the equations, you know, on this output equation? I think we have written it couple of times. Yeah, just for sake of completeness, maybe we can write it once again. So could you please write for the DC one? So DC, what would be the KVL along this loop? And here one more thing, we can assume that this IC is quite close to IE because beta is high, right? If the beta is high, then the value of alpha will be close to 1. So that way you can say that IC equal to IE. So from that, could you please write the equation KVL here? Anyone?
So 5 minus ICRC.
Okay, see here, we basically need a relation between V of CE and IC. So can you please tell me in terms of this V of CE? Then I have to write only one equation. What will be the value of V of C? Can you please tell me directly? Or expression of rather expression of V of C?
5 minus RC, ICRC.
Right. So we will take it like V1, will not write 5. So it is V1. Then see, it is V1 and here it is V2. So it will be how much? V1?
Minus ICRC.
Okay, you want to write it that way. Okay. Okay, V1 minus ICRC.
Minus RE1 plus RE2.
Minus IE into RE1, RE2.
Minus V2.
Minus V2. Okay, so here IC equal to IE that we have considered. So I am now changing it to IC, right? So that way, what would be the slope of this DC load line? What would be the slope?
1 by RE.
1 by RC plus RE1.
Should it not be a minus sign there?
Yes, so minus will be.
Yeah, yes. Then it would be
RC
RC
RE1 plus
RE1 plus RE2.
RE1 plus RE2. Very good. Right. Okay. Right. Okay. Now let us do the same exercise for the AC equivalent circuit. So can anyone please, and remember here it is small v, small c, small e, right? This is small IC, not this one, and this is small IE. So here also beta is very high, right? And because we have seen that this AC beta is very close to equal to DC beta, then that is what we are also assuming, right? And that way we can also write this small IC is equal to IE. Yeah. Now here this V of CE equal to please tell me. Yeah, what would be the KVL along this loop?
minus ICRC
Minus
ICRC minus I plus RE1.
isn't it? Right? Okay. So what would be the slope of this AC load line?
Minus 1 by RC plus RE1.
Minus RC RE1, right? And here we already know that RE2, this value is very high, right? So that way the slope and the difference between the slopes of this DC load line and AC load line, that would be quite significant, right? And the point where we are drawing this AC load line, that is basically the Q point, okay? Because this Q point basically determined by the DC biasing condition of this amplifier, right? So this is Q point. Along this Q point, you draw this AC load line, and that will basically show you how and now if you change this IB, or if you change the parameters, the input parameter, how the output parameter is going to be changed. For example, let us say that IC is now been changed in this fashion, or maybe you say no, say IB has been changed in this way. So obviously, if IB change in this way, IC will also change in this fashion, right? So the IC changes now in this way, right? So if this IC changes in this way, if you are now considering what should be the change across V of CE, then from the DC load line, you should be able to, you will, I think, make a conclusion that here this output would be look something like this, right? From the DC load line that we have discussed earlier, right? But if you now consider this AC load line, right? This AC load line, then you see that it has just cutting it here and it is just cutting it here. So that way you can see the signal or the change across of V of CE should not be the pink, should not be as shown using this pink, which we are getting from the DC load line, but it should be as per shown in this green line, which is following the AC load line. And that and why we are seeing this difference here, this type of difference probably we have not seen it earlier, because in earlier circuits there was not difference in this output loop in terms of AC and DC signal. But here for this particular case, we are seeing that there is a significant change in the output loop in terms of DC circuit and DC signal and AC signal. And that's how you are getting a difference in this load line slope, right? So
So shouldn't that be passing through origin? I mean, from the equation, VC equal to
Yes,
minus.
sir. So second quadrant, I think.
right. But here, that's what I mentioned you, na. See, this is V small c small e, this is IC, right? So these IC and IE, where we are plotting, once we have stabilized the Q point, right? Means if you have not suppose put this signal, right? Then what should be the value of VCE and IC? VCE would be this much, IC would be this much, isn't it? Are you getting my point? So
Yes,
if you remove this signal, then the Q point is here, means IC and VC is here. Then if you are now applying this signal will do a change across this point, right? Right. So for the small signal, this is the origin, not this one. This is for the DC signal.
Okay.
Okay, so you have understood, right, how this AC load line is coming into the picture and how to use this AC load line to find how the means what will be the change across what will be the change in this V of CE. Now here you can see this is V of CE, so which also signifies that it has a DC value and AC value. So that way, if you have suppose earlier biased it here, and if you have now changed IB here, now for this AC case, the change in output would be like as shown in this green lines, right? Type of green signals, AC green sinusoidal signal, right? So I hope this part is clear to you. And yeah, so if this part is clear, let us I think jump into one more quick example, and
So
let us see that, yeah, if you can answer. Yeah.
sir, in the previous, which gain shall we consider? There are two gains, right? For AC signal, the green one, which
Yes,
is
it should be the AC small signal gain only, na? So for that you should consider the AC load line only, not the DC one. DC one is only valid when and you are operating in the DC circuit. Means if you now change, suppose the battery here V1 by to a different value, then this DC load line will change, then the Q point will change. Then that Q point would be the origin for this AC load line. Then plot the AC load line and find the gain. Okay.
But sir, when we do that, we found that the gain will increase, right? I mean, when we ground the RE2.
when we this we found exactly very good question. But here from here what you are able to see that gain has reduced, right?
Yes, sir.
Right. Why so? Very good question. Good. I'm glad that you asked. Okay. Let me also ask you one question. Okay. So we are taking output across, means we are taking output from here, right? V out, right? Is first question is V out or V naught is equal to V of C?
No, sir.
No, sir.
First is this question. So you have given in the answer. Okay. Now, second question. Second question is, see, if you have this RE1 across here, right? I think I do not have much space. Otherwise, I would have shown you. So you draw the small signal equivalent circuit of this. Okay, small signal equivalent circuit of this, and then try to find what is the voltage, means how much voltage is being dropped. Okay, I think if I have some previous diagram, probably I can show it from there. 1 minute. Small signal equivalent circuit. Yes. So also you will also find if you actually draw the complete circuit from here that this Vs, okay, if you have an here two different resistances, how this Vs is distributing between Rs and this R pi. Okay, because this R pi will determine, means this V pi here, the voltage drop will determine what will be this GM V pi, what would be the current, right? So please figure it out, like what will happen if you have an one more resistance across this, I mean here RE2. What will happen? I mean, how much component of Vs will fall across this R pi, right? And from there, you will also find what would be the value of the small IC. From this, if you find what is the value of small IC, you should be also able to find what is this output voltage. So from that, you will also be able to see is the gain really increasing or the gain is really decreasing. Okay, I think I will not do it here. So you do it, in your home. But that is a very good question that you asked. But one thing, the most important thing is that this V output, yeah, this V output here is not equal to V of CE, right? Here, what we are showing is this V of CE is not the V output. That is another thing. Okay, so if you have understood this previous exercise, then please let us consider one another type of example. Here, what is the difference compared to the previous? Here we have only one emitter resistance, and the total emitter resistor has been bypassed through a capacitor C. Means so across C has been connected across this RE, right? So in AC, so you know that complete RE would be disappeared. The RE would be disappeared, right? So as you can see from here, this is the AC equivalent circuit, right? So you can see this become shorted. So that way, this point is now grounded. So it is not there. But earlier we are taking the output from here. There was no output resistance, but here we have introduced an output resistance RL, and after we have this coupling capacity, right? And we are taking this output across this resistance, right? So in AC, what will happen? This become like short, and this voltage should also become ground. Voltage should ground. This is ground. So basically, this RC and RL, they basically come in parallel, right? And this RE is now not there because it has been shorted. Okay. Now see what is happening in terms of DC. So in terms of DC, see what is happening here. We have V1, V2. Now remove this CC1, open circuit. This CE also open. The signal source is also open. So basically what we get is this one, right? So again, you do the similar analysis. So here, obviously, if you find the DC load line, right? DC load line and its slope. So can anyone tell me what would be the slope for this case? If you have understood earlier case, you should be able to tell me this.
So minus 1
Minus-
by
RC by plus
Minus 1 by
RC plus RE.
minus 1 by RC by RE. Very good. Okay, right. And depending on the value, say the Q point is here this much. Okay, say this value is say 0.8 milliamps. Say, okay, and say this value is 6 volt. Say, okay, this is the Q point value. Okay,
So will it be small IC or capital IC?
you are right. Right. Okay. So now if you look into this AC part, this one. So here, this is the Q point, right? So if you want to also now draw the AC load line. So for the AC load line, this would be the like origin, right? And now we have to draw a line. And what would be the slope of that AC load line?
Sir, minus 1 upon RC parallel RL plus RE.
Will RE be there?
RE will
No,
not
sir.
be there.
Sorry,
RE
sir.
will,
No, sir.
RE is grounded, right? So grounded means RE is shorted here, so RE is basically not there. No? So the slope is, you see, it is basically RC parallel RL. Here it was minus 1 by RC RE. So that way again you can see a difference in the slope, right? So again the swing would be different for like this case, right? If you now change this different like, and I have not plotted different IB, IC those plots like this type of plot, like this type of plot. So here also, if you do the similar type of plotting with change in IB, then you will also find this value, right? Like compared to the DC, there isn't significant change in this V of C across V of C from the AC point of view, right? Okay. So this is one way to think of this phenomenon. Okay, and the other way would be how can we connect it with the small signal analysis? Okay, maybe quickly let us do a small signal equivalent circuit of this as well. That would help us in a couple of ways. Yeah, so I am now planning to draw one small signal equivalent circuit. Okay, so where should we start? We should start with this VS, right? For say we have this VS ground, then we have this RS, then we have this RB, then we have to draw the equivalent circuit of this bipolar junction transistor. So we should have one this R pi, emitter is been grounded, so that is good. The analysis become easier, right? And this is GM V pi, and then this is RC, this is RC parallel, this is RL, and across here we are taking this V output, isn't it? Okay, so this is basically V pi, you know that. This is IB, right? Okay, so this GM V pi, right? This GM V pi can also be written as this IC, right? This is basically IC, right? This is IB, this is basically IC, right? So then can we not write here that this output voltage, that is this V output, right? V output is equal to, for this case, minus IC into RC parallel RL. Could you please check? Can I write this from the small signal equivalent circuit?
Yes, sir.
Okay. Just instead of writing GM V pi, I am writing IC, right? That's all. Okay. Now, this V output, right? V output is here, basically this one, right? And V output, if you are taking from here, is it not equal to V of C? Is V output small v not is not equal to small v, small c, small e? Because for AC it is grounded, right? So that way output voltage V output is nothing but V of small c, small e.
Yes, sir.
Yes, sir.
Right. So here what we are seeing, this, this change. Now suppose we are seeing any doing any change here, and we are getting any change in this output. So this is actually what? This is actually small v, small c, small e, right? So what I am now trying to say is that now suppose if we do any change in this input signal, right? If you follow the AC load line, that will produce, then graphically you should be able to find what is the output signal, right? The If you have to really means you have to find it type of analytically, then also you can find it in this way. That you can simply write this V naught equal to IC into, for this particular case, into RCRL, which is basically equal to V of CE, right? And you know what is the value of IC? IC, we can write it from this GM V pi, right? And for the small signal circuit, you should be able to find the value of both GM. GM, the value you can find it from capital IC, and V pi you can find from this small signal circuit. Right. Now, why I have discussed this, you will understand it immediately here. Now, let us consider one interesting topic, that is called the maximum symmetrical swing of for a particular amplifier. So what do we understand from this? Say here this signal is this much, okay, this Vs, right? So here at this output voltage you are expected to get, and output voltage means which is similar to this input signal only, right? Input sinusoidal signal only, but an amplified version, right? And if it is a suppose symmetrical signal, means symmetrical sinusoidal signal means this part, positive half and negative half, are they are symmetrical, even though from my drawing it's apparently it's not symmetrical. So consider it to be a symmetrical signal, right? Then in the output also you should be able to get the symmetrical output, right? Means both sides would be equally been amplified, because we are considering it to this amplifier to be a linear amplifier, right? So it will equally, means the amplification would be same for both positive half as well as for negative half, or it should not be dependent on the amplitude of the signal, right? And this amplifier, this C or this transistor can act as a linear amplifier when you are operating the transistor only in the active region, right? Forward active region, right? You recall, right? From this, if you have this CE character, ICVC characteristics like this, and you have the DC load line from here, then from this to this region, if the Q point is here and or the change in the Q point is here, then only it will operate as a linear amplifier, right? Or from this output versus input characteristic, that also we have seen it earlier, right? Here only in this region the transistor will operate as a linear amplifier, right? And I think earlier we have also seen or discussed this point, that what is the importance of biasing, choosing the Q point. Suppose, and we have to discuss this part, right? Q point we are expected to choose in the midpoint of this DC load line, or the midpoint of this for this transfer characteristics, right? So that we can get a maximum swing of both positive half and negative half, right? Otherwise, what might happen? Say if you have chosen the Q point somewhere, suppose here, right? And then if you have a signal, and then if you have a suppose signal like this, right? Then you see up to this region we are in the active region. So this region output would be amplified, right? Similarly, for this region, we are still in this region, active region. So this region would be amplified. This region, we are in the cutoff. So this region would be clipped, right? So that way the output would not be symmetrical, right? If this Q point is here, right? So that is what we have already discussed while discussing the biasing of and DC biasing of in bipolar junction transistor. But now what we are saying is that say we have already plotted means already kept these Q points near about in the middle. Now we are trying to see what can be the maximum swing, right? So say if this input is somewhat like this, right, then still this part is not in the active region. So that way it will not be an proper amplification in this output, right? So that thing we are now going to see from the AC load line point of view. See, it would be interesting, and now you should be able to correlate like what I have just discussed, this V of C value from this analytical model. Okay, see it here. So for that, should I draw one more plot? Okay, I will draw it. Right. So here we are plotting this IC and here V of CE, right? And our, say, the DC load line is from here. This is the DC load line. And say the AC load line is somewhere here. So this is basically the Q point. Okay. Now, and let us also assume this point same as like 0.8 and this point is say 6 volt. Okay. Now, if I ask you and say we also know from here the slope is minus 1 by RC RE. Okay. Now, if I ask you what okay, if the Q point is here uh, this, right, this is fixed like 6 volt and 0.8 volt, and if I ask you what should be the maximum swing of IC, maximum swing of IC means small I capital C, that means the DC plus AC, okay, for this amplifier. Can you answer to that question? Or in other way, if I say like what should be the maximum swing of this small I small c, means the AC value of AC signal, right, IC. So can you answer to that question?
Sir,
Hello?
0.8.
0.8. Could you please explain how did you come up with this number 0.8?
Sir, because below the, I mean, if IC becomes negative, then it would not make any sense.
Yes, but okay, then let me also give another restriction here. Say this point is say like 1.2 milliamps. Yes. Now whether 0.2 is possible? See, you can go 0.8 to this direction. Can you go even in this direction? 0.8 swing of IC?
No, sir.
No.
No, sir.
Then
Sir, we can't go till 1.2 also.
we can't go to 1.2 also. Okay.
So because then it will come in saturation region.
Yes, but here is the point. That's what I told you. You have missed this point. See, I told you this from this. You have to now see from this AC load line, right? Once you have this stabilize this Q point, right? After that, should you follow the DC load line or AC load line?
AC load line, sir.
Right. So now if you follow this AC load line, AC load line slope is much lower compared to the DC load line, right? So that means if you follow this DC load line, sorry, AC load line, then you should be able to go to the much higher value of IC, but still you will not go to the saturation, fall into the saturation region. Not clear?
No, sir.
Okay.
Sir, can we go beyond 1.2?
Yes, you can go beyond 1.2 for the AC signal.
Sir, like VCE would be the superposition of the AC voltage and the DC voltage.
Right.
Okay, yes, sir. We
Right.
can go, sir. Yes, sir.
Right. See here. This is the Q point, right? This is the Q point, right? Now, when you are going from, when you are going from higher IC or lower IC, things that you have to remember is that we should not go, beyond this V of C, this point. Similarly, we should not come here below this 0.2. You know that, right? V of C below 0.2, it will go into the saturation region. That's what we have considered, right? Okay. Now, from this slope, if you now say this car IC in these directions, right, below this Q point can make a swing of, no, it become a bit larger. So it can make a swing of 0.8 milliamps, right? Now the thing is that can IC make a swing of 0.8 in this above direction? That you have to find it out. Probably for this case, yes, because the slope is much lower for this AC load line. So it can go. Okay. And still, if you want to find it, then you can also find it from here. That's what we have written this formula. This V output equal to IC into RC parallel RL. Right. Now you know what is IC. IC is 0.8. Right. That is the maximum change in small IC, small I, small c. Right. You know the value of R, right? RC, you know the value of RL. Right. So if you can find it, you can find what is the change in V of C. Right. Then you see what is the change in V of C. Change in V of C. So that way you can find what is the change in V of C. So once you find change in V of C, so say the change in V of C is coming around 4 volts, say, okay, for a particular case. Then it is 6 minus 4 volt. That means you are still in 2 volt, okay, where you are reaching a current of 0.8 milliamps, right? Say here 0.8 milliamps. It should be here, right? It should be here. So you can make a swing up to 0.2, but it's still the transistor in the active region only. However, however, this total current is here. See, it is 0.8. Another swing is 0.8. So it is 1.6 milliamps. And this current is obviously higher than the maximum DC current. Is this point clear to you?
Sir, the AC current would lie on the green line, right?
AC current here, many lines are green. So could you please be more specific?
Sir, the line which is intersecting with the pink one.
Oh,
Yes.
okay. This means AC load line, you are trying to say.
Yes, sir.
Yes. Yes, it will follow this load line. Yes.
Sir, so what is that middle green point that you have made? 1.6 milliampere.
This
Yes, sir.
this one.
Yes. Yes, sir.
This is the total swing. If this swing is 0.8, right? So for the symmetrical, to get a symmetrical output of IC, so this should be also 0.8. So the total amplitude means the amplitude here is from here means the value of small I and small c is equal to 1.6 milliamps.
Okay, sir. Understood.
Understood?
But sir, IC should be less than the DC current.
IC should be less than the DC current. Why it should
Sir,
be less than DC current?
sir,
What will happen if it is suppose
sir,
if
from the
the
beginning we are assuming that it is a small signal.
in the beginning we are assuming it is a small signal, but this also will be dependent on this slope, right? Maybe the other way, it also depends on the like values of these gains, right? This what would be the value of this GM and G pi of this transistor. So means here this output versus this input, here it also depends on the slope of this, right? So maybe here for a very small change, the output is still in the linear region. Right?
Sir, we can write the total current as the sum of DC and AC only when the AC is small.
We can write the total current to be DC plus AC only when the AC is only when the AC is small. Okay.
Yes, sir. So
Okay.
if it is becoming larger than the DC, even then, will our assumptions be true?
Which assumption? So that's what I'm trying to pinpoint. Which
Sir,
assumption you are referring to?
sir, in the starting, that we
In
wrote
the
that VB,
starting, in the starting,
VB should be less than VT.
VB less than should be less than this, right? So does it make any, any like any? Does it impose any criteria on this IC? So please figure it out. Okay, if this you are right. If this our criteria was like V of B should be low, right? That's small. Okay, this is not that small b, small b, small b, small e. Right, this should be small, right? Okay, so but what criteria it impose on IC? First question is that, and the second question is we have also seen if it is nearly equal to 10 millivolt as well, then also the total harmonic distortion THD. Oh, it is not writing. Oh, it got crashed. 1 minute. I don't know whether it has saved or not. Not saved, then it will be a big trouble. 1 minute. Open the including automatic save changes. Okay, let's see that how much change it has saved. I should have saved it in between. I think mostly it has been saved. Yeah. No, not the very recent thing it has saved. Yeah. So yeah. So is my screen visible?
Yes, sir.
Okay. So the first thing is that our criteria was on this V of BE, right? Right. V of B. So V of B was around 10 millivolt, but still for that we were getting percentage of total harmonic distortion was around 10%. Right. So if this V of B is little bit higher, then the THD will be little bit higher. But that way, if it is for small also, then also it is, there is still small non-linearity is also present at that more time as well. Okay, because we have approximated. I agree with you. If we increase this V of B, that total harmonic distortion will also increase that way. That linearity will also lose little bit, but the total what we have imposed in the criteria, that is one V of BE. Now please correlate this V of BE, that restriction on IC. Please let me know in the next class that if you change V of B, how much this around 10 millivolt. So what is the maximum change that is possible across IC?
Okay, sir.
Okay, so with this, I think good news that we have almost completed the common emitter amplifier. right? And there are other two configurations. One is the common collector amplifier, and the other one is the common base amplifier. But I think we will not have that sufficient time, or maybe in our syllabus also these two are not that way discussed in that detail. So we will just briefly discuss. But if you have understood the CE amplifier, then you can obviously explain the behavior or amplification of common collector as well as the common base amplifier. Right. The procedure is the same. Right. For example, you can see here one common collector amplifier. So you can see the collector terminal, right? This is the collector terminal. So the collector terminal is basically, here it is connected with VCC. So that means in AC it is basically grounded, right? So collector is AC ground, right? So that's why it is called common collector. Okay. And see the output. Output we are taking across, from this emitter terminal. Okay. And across this emitter terminal, you have this RE. And here also we have used two voltage division, like voltage divider biasing to bias this base. Here is the signal source, and here is the coupling capacitor, and this is the output. So this is a basic common collector amplifier. And now if you want to draw its small signal analysis and try to find out its gain, then again the procedure is also going to be the same. First, draw the small signal equivalent circuit of this transistor, which you already know. So this is the small signal equivalent circuit of this transistor, right? Including this R0 if you are considering the output resistance, right? Means the early effect if you are considering. So this is the small signal equivalent circuit, right? Okay. Now you complete the other remaining, draw the remaining part. For example, R1, R2 is in parallel. So R1, R2 in parallel connected with the base. With this base, you have RS, VS, RS, VS. This has been connected. With this emitter, at emitter terminal, you have this RE. At emitter terminal, you have this RE, and across RE, you are taking this V output voltage, right? And here, this collector terminal is directly ground. So collector terminal has been grounded here. Right, as simple as it is. Now you have to find the gain, so you have to find V out. You have to find a relation. So if you have to find a gain, so gain would be this between V output versus V input, right? So now you can easily find it out, right? Now because it is simply the circuit analysis,
Sir,
right? You do the circuit analysis and you can find it. Yes.
sir, the positions aren't changed. Like B is B only, C is C, E is E only, right?
Which position? Terminal position?
Yes, sir.
No, terminal position has not changed.
Okay. So, sir, means common collector means the collector should be grounded, no, sir?
No, collector should be AC ground. In AC, collector is grounded. AC
So,
collector is
sir,
grounded.
what is the difference between common collector and common emitter, sir? Just the VO position, sir?
You see that in common emitter, right, you have an RC, right, and
Yes,
then you
sir.
have the voltage source. So when you're considering the AC circuit, then C collector terminal is not grounded. Collector terminal is now connected with this means collector terminal is now connected with an RC, right? And the other thing is that the output voltage is also been taken from this collector terminal only,
Okay.
right?
Only this difference. Okay, sir.
Right. And in common collector, you can see that here, this collector is AC ground and the output you are taking from this emitter terminal.
Yes, sir.
Okay. So you can find gain, do a small circuit analysis if you want to. But anyway, I will not ask any questions from this common collector. But anyway, if I ask also, you should be able to find it. That would be easy questions only. Right. It's the same similar type of analysis. Right, but we will not give much priority on this common collector. Huh? Okay, so in earlier case we have also find like how to find input resistance, how to find output resistance. So the input resistance means if you have to look from here, so what is the resistance from here, and in output resistance if you look from this collector terminal, what is this output resistance, right? Those things also you can find. Okay, similar analysis here. But here, one important thing is to mention here is that the gain for this common collector case would be positive. Remember, gain is positive. That means if the signal is like this, then here the output signal is also this is completely, this is not a good, this output signal will also will be in the same phase, unlike the common emitter case. And that is also quite prominent from here. You see that you are rising this voltage, that is rising this IC. If you rise this IC, the voltage across this RE, the drop across RE will increase. So that way V means this will increase, IC will increase, that way IC will increase, that way V output will also increase. So that way you can see that they are in the same they are incrementing the same directions. If they are increasing, so it should also increase. So gain is positive. But here important thing is that its gain is positive, but it is nearly equal to 1 unity. So that means the gain, say typical gain plus 0.978, something like that. Okay, so it will be less than 1, but it will be quite close to 1. Right. So from here you can you can really understand that whatever the voltage you are applying, the small signal voltage, you can say like at this output you are also getting the similar type of voltage. So that means here at this emitter, whatever you are getting is very means which is quite close to the input signal source. And that is the reason why this common collector amplifier is also known as emitter follower. Okay, emitter follower, because whatever you are giving at this input signal, almost the similar thing you will get at this output. Now you might ask, then what is the point, right? We are basically getting no amplification. Yes, that is true, but the advantage comes in from some different point of view. That is that input and output impedance point of view, right? And if you calculate the input impedance for like the input resistance, I would rather to say, like if you calculate the input resistance, then you will find maybe and finally we will do a comparison. I think I will show the comparison right now with you. See, this is common collector. So if you do the input calculate the input resistance, that input resistance would become very high, and the output this output resistance is pretty low, right? And even though you are not getting and voltage gain is close to equal to 1, so basically you are not getting any gain, but you are gaining in terms of current. So remember that. So here in this context, it is also important to mention how you will find the current gain, right? So current gain means the current here, say this is current is II, input current, and say here this is the current, one current would flow, here it is I out, right? So current gain you can find from this I out by II, right? So you have to find what is the input, what is the current that is flowing from this through this RS, and to find what is the current here. If you know that, then just do a taken ratio that will give you what is the current.
Sir, will IO be that current or the current through RE?
One minute. One minute. Yeah, I think 1 minute. Why you think it should be that one across RE?
Sir, because we are measuring voltage.
One minute. Huh? Actually, you are right, because see, you recall that how we have always find this output resistance when we look from this output terminal, right? So here, this is the output terminal. So we should look from this terminal. Yes. So that way, the current should be this one. You are right. So this is the expression. When you can find the current gain like this. Maybe you can just put a try. Give a try to this and see that you are really getting a current gain which is higher than 1. So then what about the common emitter case? Common emitter case, the voltage gain is already is greater than 1. That we have in many cases we have extracted that, we have calculated that. Current gain we have not calculated for this common emitter case. I request just take any amplifier that we have done so far and find what is the current gain. Please tell me in the next class, right, that what is the current gain. Say okay, I will tell you like for which example you have to do for this
Sir,
current. Hmm.
sir, current voltage gain is negative, so how is greater than 1, sir?
Okay. Okay, you are right. So is it okay now?
Yes, sir.
Okay. Okay. So yeah, mod of voltage gain, if he means basically the magnitude actually. The magnitude is greater than and 1. Current gain is greater than 1, and here but the input resistance was a bit high, but it is not that high as like common collector, so it is moderate. Output resistance also moderate to high, right? So compared to that, this common collector, it shows some criteria. I mean, some of the criteria, for example, this input resistance is very high, output resistance is very low. That is quite suitable actually in many applications. I think one of the applications I told you, if you have a very high impedance from the input side, then whatever VS you have connected, the entire VS would fall across this input resistance, means the total VS would be taken by this. The less drop would occur across this RS, the resistance associated with this source, right? So that way, very high input resistance is good. Similarly, this output resistance, okay. So if you have taken output resistance, so the output resistance is low. So that means, means if you have connected another load, suppose if you have connected another load, so mostly the entire current has been given to that load only. Okay, not very less current, right? You can consider it in this way. Say this is the output resistance, okay, of a particular amplifier. So it should be included this, and this is the load resistance, right? So it is expected to be low, because if it is low, then almost the entire voltage drop would fall across this RL only. Right. So that way, in certain applications, I know the CC amplifier is good because it can take the entire voltage as an input inside this amplifier, and at this output it can deliver almost the entire amplified version of this output, right? However, it cannot provide any voltage gain, but it can increase this current, right? Whereas the CE amplifier, it can provide both high gain, voltage gain, as well as the current gain. But this input resistance is not that way suitable for different applications. So from this, I think one thing is clear to you. Not any specific, means not any particular type of amplifier. Means suppose if you want to design one audio amplifier also, okay, which will amplify your voice, and that should be, that is driving a speaker to produce a amplified version of your audio amplitude, that signal, right? So that way you generally, in most of the cases, generally not only one type of amplifier is being used, but there are like different amplifiers are used in series, okay? Because in some cases, like criteria of matching these impedances are very important. In some portion of the amplifier, the gain is the most important thing, right? So we are not going much more detail to that, but you remember one thing, that when you are designing any particular practical amplifier, it is not only one type of either CE or CE amplifier. It is a cascade of two or maybe three even different types of amplifier. Right. So here,
Sir, Sir, current gain is IC upon IB, no sir, for
Hmm.
common emitter.
Current gain is IC by IB for or common emitter, yes, and that's why it should be greater than 1.
So sir, it means we know from the question itself, no sir, the value of IC upon IB.
Okay, okay.
Beta, it is beta only, sir. So
It is beta only. It is beta only. But you remember one thing, we have assumed something, like we have assumed that this beta in AC is closely equal to the DC beta. You remember, we have
yes
already
sir,
discussed
yes
that.
sir.
Good that you have pointed it out. We have already discussed that. But why I asked you to find it out, now you should please find it out, from one of the common emitter amplifier, what is the output, what is the output current that is actually coming and what is the input current, and really see how close it is to like what you are seeing.
Okay sir.
Okay. Okay, please do that exercise. You will understand why I am saying this. Okay. Yeah, but what you mentioned is is correct, right? For CE amplifier, the output is like IC and the input current is IB, so that is greater than 1. So for CC, you see that the same thing you can also expect from here. For CC amplifier, this current is IE, input current is IB, so IE by IB again higher greater than 1, right? But if you see for this common base amplifier, see this configuration is like this. Input current is basically the emitter current. Output current is what? Collector current. So typically IC by IB, as IC by IE. So it should be expected to be less than 1. So it's C is closely equal to 1. So you can get it from here only, right? You don't have to really calculate to, or you can easily remember this part. Okay, so similar, if you see the common base configuration, so configuration looks something like this. So common base, this base is grounded. Base is grounded, in AC signal. So that's what we have connected this CB, and this RB is being used to bias to do a biasing, for a DC biasing purpose. So RB is being used, and here these are the voltage sources just to make uh, like a base to emitter junction forward bias, this with this, and this to base to collector junction reverse bias, right? And this is the coupling capacitor through which the output resistance RL is been connected. This is the coupling capacitor through which the signal source VS is connected, right? And this is the input and this is the output. So here if we take the voltage gain, then also you will find the voltage gain is greater than 1. Current gain we have already discussed, just predicted what should be the current gain from here. But if you calculate the input resistance, so you see that input resistance is low and output resistance is moderate to pretty high. Okay, so these are some of the criteria. Depending on the required criteria at different stages of your design, you should choose which amplifier you should use for that particular purpose or for that particular stage of your design. Okay. Okay. Now this frequency response of this bipolar junction amplifier, oh, it should have been finished by this time. See, this frequency response means so far this bipolar junction transistor, we have used this hybrid pi model, which is something like this, right? It is base, emitter, collector, R pi, GM, V pi, R naught, right? Couple of things we have not considered here. For example, you see, the practical structure, practical structure, I think you remember we have started our discussion with BJT with this structure, right? That BJT basically looks something like this, right? It's N, then P, N, I'm talking about NPN, then N plus buried layer, right? And this you have emitter, base, collector, terminal, this like the terminals of this bipolar junction transistor. So here inside you can see it is emitter written as this E dash, base E dash, this is C dash. This is internal, or you can say the internal some nodes you can say. And here, like we are assuming, what is the potential at this internal nodes? The same potential is also there at this external terminals. But maybe this is not the case. When you connect any metal with some semiconductor, there will be a potential drop. So that means that will offer one resistance. between this outer lead to this inner node, right? So same thing will also happen for this base, same thing will also happen for this collector. And the things would become even worse where the doping concentration is less. So that way, the for collector, the resistance that would be offered or from this here till this point, that would be quite significant, right? Compared to this from this emitter to E dash terminal, right? So far what we have considered here, this is basically we have considered this part. Okay. Now, if you have to include in our analysis the other part that we have not considered so far, then obviously we have understood with this emitter we should include one resistance, right? We include this is the emitter terminal E dash inside, right? And this is the external terminal. So between that we should have an external resistance, right? Because of this contact. Fine. From this B dash to B, there should be one resistance. The same token we can say from this C dash to C, there should be another resistance CRC between this, right? And to isolate one device from one bipolar junction transistor to the neighboring bipolar junction transistor, generally what we do a reverse biasing between this particular PN junction. Okay, this particular P is also type of reverse bias. This junction is reverse bias. So that way you can have you can see that there is and this is basically see you apply some voltage here and make this terminal ground. Apply some positive voltage here and make this P to be ground. That way you make this reverse bias. So that means you are basically have some depletion region here, and due to depletion region you have a capacitance which is CS. So you have an with this C dash you have an capacitance which is connected with this ground, right? So C dash you have understood, right? Now this between emitter and base, this is forward bias and this is also an PN junction. So there will be one diffusion capacitance associated with this junction. So between this base and emitter, we have previously considered only R pi, but now along this R pi, you have to also consider the capacitance which is C pi. So the C pi we should also consider, right? Then what about this between base and collector? Now between base and collector, these two are reverse bias, so that there will be wide depletion layer, and they should also offer some capacitance. So it is this capacitance is between base and collector. This capacitance is C mu, right? And because of this, reverse bias, this will also offer one resistance which is very huge, pretty high actually, and that resistance is noted here by R mu. Okay, R mu is very high in terms of mega ohm, so that way you may consider that R ohm, just you can say like instead of R mu it is open circuit. That is fine. So if you do not consider R mu, so it is basically like here, it is basically open circuit, fine. However, this C mu you cannot neglect. So C mu we have to consider between this. Okay. So in our previous analysis, we have assumed that all these internal capacitances are not there. Not there means is not there means you have not considered. But when we include or incorporate the term frequency or frequency response, then we should consider what should be the effect of these internal capacitances associated with these transistors. So you have seen there are three internal capacitances: C mu, Cs, and C pi. Okay. Is this part clear to you? No response.
Sir, sir, I didn't get it.
Which part?
CS.
CS. Okay. So to isolate, CS basically the capacitance between actually this PN junction. Okay, this PN junction is been reverse bias. So how we reverse bias, this in collector we apply on positive bias. So when you apply on positive bias to a collector and you suppose you ground this P terminal, right, in the P region, right. This P region is how it look like, the P region is like this. Okay, so after that here you have again N, you have again here P, you have again here N plus. You understand? So this is again collector, this is again base, this is again an emitter. Another device will be there now on this side. Are you getting my point? Yes,
Yes,
no?
sir. Yes, sir.
Okay, right. So now this, okay, this PN junction is reverse bias and say it has been grounded in this. So obviously this will offer one capacitance. This capacitance is connect one terminal connected with capacitor, other terminal is grounded. Is it now clear?
Sir, why is there R mu?
Why is there R mu? R mu is like that's what I have said. You know, R mu, it is basically one reverse bias between this base and collector. So reverse bias also, you know, for diode we can see forward bias resistance RF, then forward bias with a battery, right? Reverse bias we have considered this is forward bias, this is reverse bias, isn't it? We have considered it like that. Instead, to make it more accurate, you should have considered one resistance here, which this resistance value is very high in the range of mega ohm. That way we can say like it is close to this open circuit. However, the current that can flow through this diode is would be very less, and the dependence of that like the current on the applied voltage will also be quite insignificant. Okay, this is for much accurate like modeling. Okay, but at the same time I have also mentioned this is at the very high, so you can consider to be as an open circuit.
Sir, why is there a resistor between E dash and E?
Between E dash E, okay, like this is again this resistance is small. First thing is that, so that way you can say like you can connect these two. But for to take account of this contact resistance between metal and this emitter, so we are considering this REX. Okay. Otherwise, you can also make this two shorted. That will this resistance value is expected to be quite low for a good design.
So same for B dash and B.
Same, no, for B dash it is not. See, B dash we have considered that you know the node point here, but if some current has to flow through this, then their path is bit longer here, right? From here to here. At the same time, the doping concentration of base is lower than the emitter. So the resistance offered by this path would not be that way negligible as we have neglected for the emitter.
Okay, sir.
Right? Okay. So how are you doing on time? It's 9:40. My God. So you see, this is again CE amplifier, and this, suppose for this CE amplifier we are doing the analysis like frequency response analysis. So now we have fixed say the amplitude of the signal, but we are varying the frequency of the signal, right? And then we will see that what is happening here. So in earlier case, what we have considered that the frequency we have in earlier case we have fixed the frequency, right? And we have chosen the frequency such that, remember, and please notice this word very carefully. In earlier case, means so far whatever we have you know discussed, there we have fixed the frequency. So fixed the signal frequency. Okay. So how we have fixed? Here is a start. So we have fixed the frequency such that the coupling capacitors, this bypass capacitors, okay, they are short circuit. Okay, this and this, they are short circuit, and BJT internal or parasitic capacitors are open circuit. That means the capacitances associated to this junction and this junction, they are open circuit, right? Because why we have taken how could have we have taken this criteria, because the values, typical values are in the range of microfarad. CC1, this all this external capacitances. Whereas this internal or parasitic capacitances associated with this BJT, they are in the range of picofarad. So pico means 10 to the power minus 12 farad. Micro means 10 to the power minus 6 farad. Now, if you see what is the react and impedance offered by an capacitance, this is basically omega C, right? So we have chosen the capacitance, means choosing the frequency such that this for this capacitance value, for this microfarad range of values of the CC1, CC2, CE, etc. These values are pretty low. That means short. However, for picofarad, when you have taken this picofarad, the impedances offered by this XC is pretty high, such that the impedances offered by this capacitances we have considered to be as open circuit. For example, you can see it here. If this is open circuit, so that means this C pi is not there. If this is open circuit, if it offers that high, that much high impedance, then it is again open circuit. So that means C mu is not there. If similarly this C mu S is not there, then you see the remaining circuit. If you do not consider this external RC, R pi and all this, then it is basically similar to the hybrid pi model that we have used without capacitance. But now for this particular case, we want to see how the circuit behaves when you change the frequency. Okay, so now the frequency has been changed from very low, it will go, and then we will go to very high. So we are now changing that frequency, right? Now see what is happening when the frequency, see this we are this is the gain, we are plotting here gain versus frequency, and frequency is in log scale. Okay, otherwise we cannot accommodate a huge range, huge change in gain, frequency here. What do you mean by huge change in frequency? For example, say you can plot this frequency, and suppose if you are plotting up to say 400 kilohertz. Okay, so if this is 400 kilohertz, then obviously this is say let me say this is 200 kilohertz, and this is 100 kilohertz. 100 kilohertz. Then here the 10 kilohertz is here, right? So suppose something is happening, some change in gain is happening, say at say 100 hertz. Okay, suppose something is happening at 100 hertz. Then where is 100 hertz here? Here. Now suppose something is also happening here 500 hertz. Where is 500 hertz? Almost in the same position, right? So if you plot it in a linear scale, then you cannot show the change which is happening for the lower range of frequency. Okay, so we have chosen the log scale here to demonstrate what is happening throughout the entire range of frequency. So you see this gain we are plotting in dB. Now we have already done the this part, what is called that filter part. So we are already you are already familiar with this dB concept, right? So say this is a particular dB, right? And we are plotting it gain, and we are now changing the frequency. So we have started with a very low frequency. So what will happen at this very low frequency? Again, see from here. So earlier we have said we have chosen some frequency in this range such that omega c, 1 by omega c is becoming very low. It is negligible. But when the frequency itself is very low, this frequency itself is very low, then that means X is higher, right? So that way, these impedances, like the impedances offered by this coupling capacitor and all this stuff, you cannot really neglect them. You cannot really say that they are short circuit, right? So that means you can assume you have an impedance here along with this RS. So there will be some amount of voltage Vs will also be dropped here, across here. So the amount of voltage dropping across this V of BE, that would become less. So that way the gain will also fall down. It is not difficult to understand. So that way, when the frequency is very small, the gain is very small. As you are increasing the frequency, this XC is decreasing lower and lower. So that means we are going closer and closer to this short circuit case. So that's why gain is increasing at a particular point, at a particular frequency. You can assume that like these are short circuited. So when you consider them short circuited, the gain will remain flat. So the gain will remain flat, after that remain for certain region, okay, certain frequency range. After that, when you go for very high frequency, then see what is happening. Then these internal capacitances here, the internal capacitances values are in the range of picofarad, right? But again, and that is why this internal capacitance earlier we have assumed to be an open circuit. But now see what is happening. This is low, right? I understand. But now we are increasing omega, right? So that way, this value of XC is also falling down, right? So when the frequency is very high, then these internal capacitances you cannot neglect any further. So you have to consider that. So when you consider that, then the total circuit would become something like this, right? And if you we are not going to discuss it in much more detail in your book. The entire derivation is given. The expression considered of output voltage versus input voltage, considering this all the capacitances. If you are interested, please look into that. And if you calculate, you will see the gain actually falls for very high frequency. So in the mid frequency range, where the gain is somewhat constant, there this is the mid frequency range. Okay, so here it is the low frequency and here it is high frequency. Okay, and compared to this, if you go to 3 dB point below, right, then you will get this FL, lower cutoff frequency, and here it is the higher cutoff frequency. And if you want to find what is the bandwidth, so the difference between FH and this is the bandwidth. This is the bandwidth, means for this entire region, this frequency range, this transistor, the gain of this transistor will remain more or less flat. Right, this is what it has been shown from this plot. Yes, yeah, more or less, we have covered this frequency response. And as I mentioned, I'll also share with you one video from the lab that that I have made. So please look into that video, and things would be much more clear to you when you see its practical demonstration. Yes. So any doubt?
Sir,
Hmm.
sir, in the above diagram, where you have shown the capacitance. Yes, sir.
This one, you were referring to the small signal circuit or this circuit?
Small signal circuit.
Huh?
Small signal circuit.
Okay, this one.
Sir, here base and capacitor are forward biased, right? PN.
Base and emitter is forward bias. Yes.
Oh, sir, here from P to N, base to capacitor, sir.
Base to capacitor.
Yes, sir.
No, base is this. Then base to which terminal you are referring to?
Capacitor terminal.
Capacitor or collector?
Sorry, sir, collector.
Base to collector. Yeah, okay. Base to collector
Is forward bias. P to
no,
N.
reverse bias. What are you saying? After finishing this, when you are going to finish this BJT, this is always reverse bias. This is always forward bias for active, to keep the transistor in this active mode, forward active mode.
Yes, sir. Okay, sir. Here we maintain voltage. Yes.
Yeah. So, but to make this forward bias, what you do, you have to keep some positive voltage here, right?
Yes, sir.
and that will make this PN junction reverse bias. And that is the source of CS. I don't know whether you were asking this question or not, means, or which question you are referring to from here?
No, sir. Now it is clear.
Now it is clear. Okay.
So I did not understand why the gain falls at high frequencies. So because XC will keep on decreasing if we increase omega.
XC.
So
Where is
for
XC? Where is
sir in
XC?
the CE amplifier,
Huh?
so that for
XC
any
is
capacitor,
yeah, but yeah, this capacitance you were referring to, external capacitances.
so
Are you referring to
internal one, sir, of the
internal ones?
transistor.
Okay, internal ones. Okay, this is yes, internal ones. They will yeah. With you are right. If the frequency is changing, their impedance will fall.
So
If the
still
frequency is increasing, yes.
they are connected in parallel with these resistances. That's why we cannot neglect. Is that the reason?
Could you please repeat it again?
Sir, I mean, why are we neglecting the means? Why is the gain reducing at high frequencies?
Yes. So what was your you have made some point, right? What is your point?
No,
Like
sir. This is
earlier
the
you
question.
mentioned na, that okay, this is the question. So you know, it is see, one way to look into it, just to very just to understand it quickly, you can probably look into it like this. See, this is C pi, right? C pi is in parallel with this R pi, right? Okay, C pi is keep on falling with increasing frequency. C pi is in parallel with, so overall impedance across, like from this node to this node, is actually falling, right? So that means V pi is actually falling. V pi
Okay,
falling
sir.
means this is falling, right? I am just trying to say it from like some very easy from very easy point of view. But if you are interested, in your book, the I this derivation is there, so you can probably look into that, and it should be clear to you from there. But one easy way to understand it, like from here, you can say like V pi will fall, right, with increasing frequency, because
Yes,
this.
sir.
Okay, so no doubt, right? Okay, then I think with this we have finished this part, the frequency response of this BJT amplifier part. So I would like to have a small class, maybe around 30 minutes, to complete the problem sets in practice paper 4. So please let me know when can I have that time. Maximum 30 to 35 minutes, not more than that.
So the syllabus will be till today's class, or is there something that you will teach?
That I will tell you in the next class.
Sir,
Okay.
so after Thursday, you need minutes, right, sir?
After Thursday means?
Sir, tomorrow is also one lecture, no, sir?
Huh. Oh, tomorrow
So,
is yes. Tomorrow we have a class. So
yes.
probably then tomorrow. Okay, when is your second exam supposed to be?
Sir, next Wednesday for EC, because on that day 2 hour slot is there.
Oh, next Wednesday. Okay. Okay, then I think tomorrow we will start with MOSFET. Okay, and I need one extra sometime, just half an hour to finish this tutorial part.
So please take tomorrow's class only because we have uh, a lot of preparation for the exam.
Is it?
Yes, sir.
Okay. Okay, fine. Then tomorrow we will finish first quickly the practice paper, and then we will see that if we can start the MOSFET. Huh?
Sir,
So
syllabus would be till here, no, sir?
yeah, looks like, but I will tell you tomorrow. Okay.
Okay.
And one more thing is that yeah, and one more thing is like for tomorrow's class, I will before tomorrow's class means after means today only, just after this, I will share the solutions, okay, of practice paper 4. So I hope that you have already tried to solve the problems. So please check those problems, and so that tomorrow maybe quickly we can finish the practice paper 4 and start the MOSFET. Okay, is that fine?
Yes, sir.
Yes.
Yes,
Okay.
sir.
Okay then. So thank you.
Thank you, sir.